Hi everyone, today we're going to be talking about systems of equations. A system of equations exists when two or more equations overlap at a specific point, infinitely many points, or no points at all. In this section, we will be looking at two different ways to solve a system of equations, either by elimination or by graphing. The observations you make about the systems of equations will help you identify what type of solution you have. Below are three different types of solutions you will encounter in this course. So here in this first image, we have that there is one solution. The lines intersect. Intersecting lines have one point in common. There is one solution to this system. So sometimes you'll hear it called consistent independent. The second scenario in the middle is when we have no solution. This means that the lines are parallel. Parallel lines have no points in common, and there is no solution to this system. Sometimes you'll hear this called inconsistent. The last scenario is there are infinitely many solutions. Both equations give the same line. Because we have just one line, there are infinitely many solutions. So as you can see here, it looks like there's one line, but sometimes the way that you can think about it is that there's actually two lines and they are on top of each other, and so they are intersecting everywhere. And sometimes you'll hear this called consistent dependent. How do we tell them apart? It is likely you have seen these types of linear equations before today. What do you notice, and what do you wonder about these three types of solutions? Take a moment, pause the video, and try to think of when these three different scenarios might occur. With one unique solution, you will have one and only one point at which the two lines intersect. These systems are called consistent or independent systems of equations. List an example of a system that has one solution, graph your work, and also solve by elimination. Now, if you're familiar with this, you can make up your own system of equations. I'm going to give one for us, but feel free to use a different one if you'd like. So I'm going to start off with 2x plus 3y equals 6, and x minus 2y equals 8. Now, notice that these are not in the form that we are traditionally used to. These are in standard form. So just as a quick reminder, standard form looks like ax plus by equals c, and we are more used to using slope-intercept form, which is of the form y equals mx plus b. So it's not too complicated to convert these into slope-intercept form. We just need to solve these equations for y. So in this first equation, I'm going to subtract 2x from both sides, and if we do that, we get 3y equals negative 2x plus 6, and then from there, if I divide both sides by 3, then I would get y equals negative 2/3 x plus, and when I was in algebra, my teacher would always say, I heart algebra, and she'd make a little heart like this for when we had examples like this, just to make sure that you're dividing the bottom term into both terms in the numerator. So 6 divided by 3 is 2. Okay. Now for this next one, we also want to convert this into slope-intercept form. So I'm going to subtract x on both sides, and we get negative 2y equals negative x plus 8. And then if I divide both sides by negative 2, then we get y equals 1/2 x minus 4. So now that we have our two equations in slope-intercept form, let's go ahead and graph them on the grid that's provided up to us on the left-hand side. So the first equation has a y-intercept of 0, 2. So I'm going to plot a point at 0, 2, and we know that the slope is -2/3, which indicates that I want to go down 2 units and 3 units to the right, which will end me right there. And we only need 2 points to create a line. If you want to do more, you absolutely can. I'm just going to connect these with a line with my ruler, and then let's graph the other equation. We have y equals 1/2 x minus 4. That has a y-intercept of 0, -4, and then the slope is 1/2. So I'm going to go up 1 unit, right 2 units. I'm going to connect those. And I'm just going to put arrows on all of my lines to indicate that they are going forever in both directions. Now, the solution to this system of equations is the ordered pair where the 2 lines intersect, which is happening right here. Now, the downfall of graphing in this particular example is that the ordered pair where they intersect is not a whole number, and so we're going to have to estimate it. It's looking like the x value's about right here, so let's count over. This is 1, 2, 3, 4, 5. So it's going to be some number between 5 and 6. I'm going to estimate that the x value is like 5.2, and then the y value is about right there, and I'm going to estimate that to be maybe -1.8. We're actually going to see that the -1.8 is a little bit off because I didn't do the greatest job of drawing my lines to the best ability. What's nice is that we'll be able to use algebra in order to solve for the exact solution, and then we can compare it to the solution here that we approximated by graphing. So sometimes graphing works out really nicely if the point where they intersect is a whole number ordered pair, but here, because the x and y coordinates are not going to be whole numbers, it's not the best way of going about solving this system of equations. So we're going to jump into talking about what's called the elimination method. And the reason it's called elimination is because our goal is to eliminate one of the variables, and we do that by either adding or subtracting the 2 equations together. Now, before we can add or subtract, we need to make sure that the coefficients for one of the variables is matching, so that when we either add or subtract them, one of the variables is going to be eliminated. Now, if we added or subtracted the 2 equations together as is, neither of the variables are going to be eliminated. So what we need to do is I'm going to take this second equation and I'm going to multiply the entire equation by 2. Now, in your mind, you should be able to convince yourself that that's okay, because as long as I do something to one side of the equation, as long as I do it to the other side as well, the equation will still remain equal. You can almost think of it as like a balance. If you start off with balance, as long as you add or multiply something to one side, if you do the exact same thing to the other side, it should remain balanced. So I'm going to go ahead and multiply that second equation by 2, and if I do that, my new equation would be 2x minus 4y is equal to 16, and I'm going to keep my first equation the same, and I'm going to keep it 2x plus 3y equals 6. Now, what we can do is we can subtract these 2 equations, line them up with the correct variable and constant values, and we could subtract. And what's going to happen is 2x minus 2x gives us 0, 3y minus negative 4y gives us 7y. And then 6 minus 16 is negative 10. And so we get the equation 7y equals negative 10, and I can divide both sides by 7, and that will give me y equals negative 10 over 7. Now, if you throw that into a calculator, you get negative 1.428. So notice that I was a little bit off in my estimation because I thought the y-coordinate was about negative 1.8, and it's probably because I didn't draw my lines as great as it could have been. So now we have the y-coordinate of our two lines where they intersect, and you can take that y-coordinate and plug it into either of the original equations to solve for x. So I'm going to go ahead and take that and I'm going to plug it into that equation right there so that I can solve for x. So if I do that, I get x minus 2 times negative 10 over 7, which is equal to 8. And then if I multiply negative 2 and negative 10 over 7, that's going to become x plus 20 over 7 is equal to 8. And then I will get x equals 8 minus 20 over 7. And you're welcome to just throw that into your calculator if you'd like, or you could find a common denominator. So 8 is the same thing as 56 over 7 minus 20 over 7. And that is going to be 36 over 7. And 36 over 7 is equal to 5.14. So that's closer to what I guessed or approximated earlier. It was 5.142, and I approximated it to be 5.2. So if you wanted to present your answer in an exact manner, then you could either say x equals 36 over 7 and y equals negative 10 over 7, or you could also present your solution as an ordered pair and say 36 over 7, comma, negative 10 over 7. And that is our answer to this system of equations.